Recording. Good. It works. All right, so it's time to BOTC, which of course means to bust out the calculus. Get out the good stuff. So let's say that we have a graph of X and Y, but we sketch something in parametric. I'll just say, let's say we start here, and let's say it moves through like that. We no longer have to limit ourselves to motion along a straight line, left and right, up and down. We can now travel through the coordinate plane through 2 dimensions instead of just 1 dimension. And in this case, this one I drew started over here. It mapped out in that direction with the arrow showing the direction. The speed you really couldn't discern, but that's where the calculus comes in. We'll quantify that. And of course, the path is the shape itself. So notice that is not a function of X, right? It's not a function of Y in terms of X. It fails the vertical line test. But what it is, it's a function of Y in terms of T and X in terms of T. But if this particle, if you want to think about this as a particle that travels along this curved path, if this particle, let's say, as it was making this corner, went whoa, and broke out of its orbit, it would fly off at what we call the tangential velocity and direction, right? And you could extend that tangent line all the way through there. So the tangential velocity is the speed of the object in the particular direction at any given moment. But we can break it down into its components. So we're going to be finding slopes of tangent lines still as dy dx. We want to know how fast this thing is traveling vertically with respect to the horizontal. But it's going to be a function of t, right? Which is interesting. Our derivative is going to be a function of t. But we still want dy dx. So here's how we do it. If I'm interested in dy dx, that is how fast the vertical is changing with respect to the horizontal, and I have 2 equations that are parametric, I'll just take the derivative of the first one. I'll take the derivative of y with respect to t, and I'll divide it by the derivative of x with respect to t. Now the reason this works is simple algebra. Stay, change, flip, right? Dividing by a fraction is the same as multiplying by the reciprocal. And if you do that, you notice that your dt's essentially divide out. Okay? So you can shorthand that. You could say that that's going to be y prime of t over x prime of t. That's another way to do it with function notation instead of Leibniz notation. All right? So notice that both the first and second derivative are still functions of t. But we're still taking the quotient of y to x. And of course, dx dt can't be 0. So that'll give us the velocity, the tangential velocity, if you will. We'll call that the tangential velocity. Whereas y prime of t and x prime of t are your 2 component velocities. All right? Now, we also might be interested in the acceleration of this object through this curved path, and that would still be the second derivative. So the way that we're going to find the second derivative of y with respect to x, not with respect to t, we're still going to take the derivative of both sides, or both the top and bottom with respect to x. I'm going to forego all of that stuff right here and just jump to the end. If you want to follow the algebra, that's great. To take the second derivative with respect to t, because that's going to be our independent variable, as I already mentioned, we're going to take the derivative of the first derivative, but we're going to have to divide through by dx dt, or x prime of t. Just like over here when we took the first derivative of y, it was the derivative of y with respect to t divided by dx dt. Those might not be ready, but you could try. I just put them in this morning. The second derivative is going to be the derivative of the first derivative, but each time we take the derivative, we're going to have to divide through by another dx dt. Okay? So the third derivative would be the derivative of the second derivative divided by another dx dt. And that's really one of the few things you have to remember that's a little bit different. Okay? So let me show it to you how it works. It says without a calculator, given this and this, we want to find dy dx and the second derivative evaluated at t equals 1. Now, I say without a calculator, but because I wrote the question, I could change the question. So let's go ahead and look at it from a calculator perspective first. If you change your mode to parametric, which I already did, and you go to y equals, remember you have 2 equations there, you can type them in. If you hit zoom 6, you'll get this graph right here. And it traced out very, very quickly. So let's go to the window. If you notice, the standard T min is 0 and the standard T max is 2 pi. believe it or not. And if you want to slow down the graph, we talked about changing your t-step to something smaller like 0.01. Did that work? We'll leave all the others. So let's see it now. Now you can kind of get an idea of how it's tracing out. All right, so if you hit the trace button, and we said when t equals 1, type in a 1. It'll give you a t input there. You are showing now where you're at. So we're at the coordinate 2, 1. I want to know right there if this particle that was traveling along this curved path, if it were to break out of that path and fly off, without anything else affecting it, it would fly off at a tangent. What that dy dx tangential velocity is, there's one way to do it on your calculator. Just like we did before from the graphing screen, you can hit second trace, and you have a brand new window here. We want dy dx. So if you hit 2, you can now type in a value of 1, and you get the dy dx value to be what? It's actually 4, okay? So what that means is at that moment, that particle is traveling 4 units vertically for every 1 unit it's traveling to the right. So its vertical speed, or vertical velocity, would be 4, and its horizontal velocity would be 1. Okay, we're just taking the quotient of the two. So let's verify that. Let's verify it. All right, so how are we going to find dy dx? Well, here we go. You could do it one of two ways. You could say dy dx is equal to y prime of t over x prime of t. That would be great. And then you could just do the derivative twice. So what's the derivative of y? If y is 3t squared minus 2t, it is 6t minus 2. Okay? And then x prime, we'd have to use the power rule. So it's going to be 1/2 times 2 is 1, t to the negative 1/2. So 1 over the square root of t. That's the derivative of 2 square root of t. There it is. Now, if you wanted to simplify that, state change flip, you get the square root of t times 16 minus 2. And so here we have an equation that gives us essentially the tangential velocity, if you want to think about it in terms of motion, in terms of t. So now if we want to figure out what dy dx is when t equals 1, we'll use Leibniz notation, dy dx at t equals 1. We plug it in, we get the square root of 1 times 6 minus 2, which of course comes out to be 4. If you were to look at those two units separately, y prime of 1, just plug it into 16 minus 2, you get 4, and x prime of 1 is 1. So at that moment, you could say one of two things. The particle is traveling 4 units vertically. For every 1, it's traveling to the right, or it's traveling through the curved path at 4 units per unit of time. Okay, now the second derivative. The second derivative is still going to give us the curvature with respect to x. How are we going to find the second derivative if our first derivative is a function of t? Well, it's going to be the following. The second derivative of x is going to be the derivative of the first derivative. So how would I take the derivative of this with respect to t? Product rule. Good. So let's go ahead and do that. The first factor is square root of t. That's really t to the 1/2. So it becomes 1/2 t to the negative 1/2 times the second factor just goes for the ride. So it's 6t minus 2 plus then it's the square root of t times the derivative of 6t minus 2, which is just 6. So because we're taking the derivative with respect to x and not with respect to t, I can take the derivative of the derivative with respect to t, but then I have to divide through by another dx dt, which is this guy right here. So I have to divide through by another 1 over the square root of t. So every time you take a subsequent derivative with respect to x, it's the derivative of the previous divided by another dx dt each and every time. So if you wanted to clean that up, state change flip, you would get the square root of t times 1 over 2 square root of t. I guess 16 minus 2 could be in the numerator there. So I'm moving through the algebra here a little bit quickly, but the idea is that we're combining two derivatives here. So distributing now, we get 6t minus 2 over 2 plus 6t. So there's kind of a cleaned up version of it. Or even more, you could say it's 3t minus 1 plus 6t, which combines to give you 9t minus 1. So all that hard work allows you to find one of two things. If you're talking about it from the Leibnizian perspective, this is still a way to determine what the curvature of the graph is. But from the Newtonian perspective, this is the acceleration of this particle through two-dimensional space, which is really kind of nice. Let's go ahead and see what it is at 1. So we'll say the second derivative of y with respect to x at t equals 1 is now 9 minus 1, which is 8. So the particle is accelerating by 8 whatever units of distance per time squared. And of course, because it's a positive, we know that the curve is concave what? Concave up, yeah. So if you want to go back to the graph and take a look, it is concave up there. Pretty nice. So there's parametrics. You're just breaking this, you have something traveling on a curved path. You break it down to the component velocities, but the dy dx is kind of like your resultant vector velocity. We're going to talk about resultant vector here shortly. All right, let's look at another example. Example 5. Without a calculator, given x equals 4 cosine of t and y equals 3 sine of t, write an equation of the tangent line to the curve at the point where t equals 3 pi fourths. All right, now when it says tangent line to the curve, that's going to be the exact same thing because, once again, you're graphing this in terms of x and y, and it's going to trace out in a certain fashion. In fact, if you want to see what it traces out, let's see where it starts. If I let t equal 0, what are my x and y coordinates? What's the x coordinate when t is 0? 4. Yeah, good. And what's the y coordinate? 0. So this graph is starting over here at the point 4, 0. And what you'll see it do is it traces out like this. And then it'll come back around full circle. Okay, you can verify that on your calculator. But it traces out once from 0 to 2 pi. As t ranges from 0 to 2 pi, this thing traces out. But this is going to be 4 units, and this is going to be 3 units. So it's not really a complete circle, but rather it's a, what do you call those circles that don't have the same radius? Not ovals, but ellipses. Right. So this actually ends up being an ellipse. But all that aside, I want to know when t equals 3 pi fourths, what is the slope of the tangent line? Well, 3 pi fourths is going to be over here. It's kind of like the unit circle. I want the equation of that tangent line. So what do we need for the equation of a line? Point and a slope. So let's go ahead and find the point. The point is going to be x of 3 pi fourths, comma, y of 3 pi fourths. We just got to find both of them separately now. So what would be the x coordinate? Cosine of 3 pi fourths is negative square root of 2 over 2 times 4 is negative 2 square root of 2. And then sine of 3 pi fourths is positive square root of 2 over 2. So you get 3 square root of 2 over 2. So as you can see right there, we are in quadrant 2. We're left and up. So I have the point. Now I just need the slope at that point. How do I find the slope at the point? Derivative, yeah. Now last time I said there were 2 ways to do it. We went straight toward the ratio. Here's the other way to do it. You can actually find your component derivatives first if you want. X prime would be negative 4 sine of t. And y prime would be 3 cosine of t. Yeah? So what would x prime of, what time are we at? 3 pi fourths? So x prime of 3 pi fourths, if you wanted to plug it in, it's going to be negative 4 sine of 3 pi fourths, which is square root of 2 over 2. So it ends up being negative 2 square root of 2. And then the vertical velocity at that moment, if you will, is going to be 3 times negative square root of 2 over 2, which ends up being negative square root of 2 over 2. So what we can say, just based upon this numerical evidence, is at that moment, the particle is moving which way horizontally? Left, and it's also moving vertically down. But it's not actually moving straight horizontally or straight vertically. It's moving through a curved path. but that's kind of its net movement. So at this point right here, you can discern that the particle is traveling in that direction. Okay, that's how it's kind of traced out, if you will. It's actually traveling along the curved path. So how do we find the slope then at that point? Well, dy dx then, when t equals 3 pi fourths, is just what we just found up here. It's going to be that number, which is y prime at that point, divided by the other number, negative 2 square root of 2. And if you simplify, your square root of 2's will divide out, and you end up with 3/4. Now, is that a reasonable slope for that line? Yeah, it's a positive sloping line. So notice that even though the particle is traveling kind of down and to the left, we still say that the slope of the tangent line is 3/4. So the particle, that would be the speed. The particle is traveling at 3/4 units per time in that direction along that curved path. All right, so the tangent line itself, we need to finish. The line is going to be y equals the y value, which we just found to be this wonderful number, 3 square root of 2 halves, plus the slope, which is 3/4, times x minus, which becomes plus the x value. So the same skills we've been doing, just doing it twice. Once for the x, once for the y. All right, questions so far on that? Let's talk about something else real quickly here. I don't know if y'all studied this in Algebra 2, but the equation of an ellipse centered at the origin, which is what this is x squared over a squared plus y squared over b squared equals 1, where a is the x radius and b is the y radius. So with that in mind, if you know that the x radius is 4 and the y radius is 3, we can actually write the rectangular equation for that ellipse. It would be x squared over what? The x radius is what we're calling a, and it's 4, because from the center we go left and right 4, so that would be 16, plus y squared over 9. Yeah. This is the equation in standard form for an ellipse centered at the origin. We can actually arrive at that equation by eliminating the parameters. So let's kind of throw this lesson in here as well. We did that on the very first example, but it's a little bit different when you have trig functions. You have x equals 4 cosine of t and y equals 3 sine of t. It's going to be kind of ugly to solve one of those for t and to plug into the other, which is what we did last time. So is there another way to relate cosine to sine? Do we know an equation relating cosine and sine that works? Like an identity, maybe. A PID, right? We have the PID that says cosine squared, I'll use t, plus sine squared of t must equal 1. So let's go ahead and solve the first one for cosine. Cosine of t, if we divide through by 4, must be x fourths. And sine of t, if we solve for it, must equal y thirds, yeah? And because it's an identity, it works for all values. So let's go ahead and substitute in. Cosine squared is now going to be x over 4 squared, plus sine squared is now going to be y over 3 squared. And it equals what? 1. So if I simplify, I get x squared over 16 plus y squared over 9 equals 1. And that is, in fact, the exact same thing we generated from knowing the equation. So there's lots of different algebraic techniques for eliminating the parameter. But remember, the rectangular coordinates, just in terms of x and y, only give you the tracks in the snow. You would just see the ellipse. You wouldn't be able to figure out in what direction they were traced out or how fast they were traced out. But writing it like this in parametric form gives you those two other characteristics. Very important. Yes? Are Newton's kinetic equations derived from vector calculus? What's that? Like the unit of Newton, like a kilogram meter per second? For the most part, yeah. Newton's motivation for discovering was motion. Yeah. I think he probably worked with parametrics. Yeah, working with linear motion first, which would be just like x of t, something that moves horizontally, and you can apply it to y of t, and then you combine the two, and you have a two-dimensional movement. Yeah, which could easily then be closely related to the discovery of his physical equations. It's hard to know, yeah, but he certainly did think in two dimensions easily, yeah. Which of course is vector. This is essentially vector calculus. Okay, parametrics and vector calculus really one and the same, just two different packagings of the same information. All right, before we get to vectors though, let's look at a question like this, which will very similarly feel like an implicit differentiation type question. Without a calculator, find all the points of horizontal and vertical tangency for this set of parametric equations. So you have an object that is like moving maybe through space, maybe it's traveling like that, you know, and there would be the direction that it's traced out. You want to know where is still on the coordinate plane, where do we have horizontal tangents and where do we have vertical tangents, right? This one has several. So we still want to know where does dy dx equal 0 and where does dy dx equal non-zero over 0. So to do that, we're going to need the derivative. So let's go ahead and do it the first way that we did. Dy dx equals y prime of t over x prime of t. I kind of prefer to use function notation there instead of Leibniz, because Leibniz notation then becomes kind of a complex fraction. So let's go ahead and create the derivative function first. What's y prime of t? 2t minus 3. Excellent. And then x prime of t is 2t plus 1. So there you go. We have a first derivative of y in terms of x as a function of t. I now want to know where is dy dx equal to 0. Just like before with parametrics. So since we have it as a quotient is equal to 0 when the what's 0? The top, the numerator. So 2t minus 3 equals 0. That's going to be when t equals 3 halves. So again, you could think of t in terms of time. It's kind of convenient. So this would be essentially like 1.5 seconds, or at t equals 1.5, this object is moving 0 vertically, right? Horizontal tangent means it's not moving up or down. It could still be moving left or right through the plane, but it's not moving up or down. And then the other one would be when dy dx equals non-zero over 0, because a vertical tangent would be where we have slopes of plus or minus infinity. That would be where the particle is moving up and down now, possibly, but not left or right. So we set the denominator equal to 0. And that would be when t equals negative 1/2. So really, what are we doing when we find these points of tangency? We're looking to see where the vertical velocity is 0, where it's not moving up or down, could still be moving left or right. That's the horizontal tangent. And we set for the vertical tangent, we set dx dt, or x prime equals 0. That means when it's not moving horizontally, it could still be moving up and down. Vertical tangent, horizontal tangent. And of course, that's the value of t, but if it asks you to find the points, that kind of implies x comma y, doesn't it? So once you have your t values for each, how would you go about finding the actual coordinates? Yeah, you would plug these right back in up here. So I won't do it for both, but in this case, the horizontal tangency point would be at 3 halves squared plus 3 halves, comma, 3 halves squared minus 3 times 3 halves plus 5. You just plug them back into your original x and y. And that's not going to be a really pretty number, but that would be the x and y coordinate then on the coordinate plane. Okay, so let's revisit then arc length. And we've been kind of talking about motion the whole time. So let's say I have a particle that moves along a curved path that looks like that. If I wanted to figure out the arc length, that is the length of the curve, then in terms of motion, that would give me the what of the object? Total distance traveled. Good. So in this case, the curve length in parametrics gives you the total distance traveled. Not the displacement, but the total distance it travels. Okay? So here is the formula for parametric arc length. It's very, very, very similar to rectangular arc length. Okay? Remember, rectangular arc length was the following. I'll write it underneath here. It was the integral from x equals a to x equals b, square root of 1 plus f prime of x squared. We just did that. You're still taking the derivative, and you're still squaring it, but you're going to be doing each of them independently. So it's now the square root of x prime squared plus y prime squared. Instead of 1 plus, it's each of them squared dt. Okay, so not that difficult to remember because it's very, very similar to the other one. And not only does that give you the arc length from A to B, as you'll see in terms of particle motion when we get to vector, it gives you the distance it travels. So moving very quickly still today, without a calculator, find the arc length of the given curves if you have those two set of parametric equations. And here you have an interval for t, which is kind of nice. Because if you weren't given an interval for t, you wouldn't necessarily know which length to give. Okay? So let's go ahead and get our pieces all lined up. X prime is 2t, and y prime is 12t squared. So now, here we go. The arc length is going to be the sum from what to what? 0 to 1. Yeah, our functions are all in terms of t. So it's from t equals 0 to t equals 1, square root of x prime squared plus y prime squared. So we'll just drop them in there, 2t and 12t squared. Now, it's said without a calculator. So just like with rectangular arc length, this should simplify down to something that's manageable. Let's see what we get. We get 4t squared plus 144t to the fourth. And what do you notice I can factor out from each of those under the radical? A 4t squared, good. And that leaves me a 1 plus 36t squared. Now, why is that important? 4t squared as a factor is a perfect square, isn't it? So that, oops, I put an equal sign there. That's not the right place for it. I can factor that out from under the radical and call it a 2t outside the radical, and that leaves a 1 plus 36t squared under the radical. And because I'm going to integrate it, maybe I'll get rid of the radical and call that what's left to the 1/2 power. And now we're back in section 4.4. You have a product. The 2 goes along for the ride. Your inside function is 1 plus 36t squared. What's its derivative? 72t. We get the critical t. We're only off by 72. So we have a correction of what? 1 over 72. Good. 1/72. And now the 2t is taken care of. The t gets packaged back up, and now we're on to the rule of integration, which is blob to the 1/2. So it becomes blob to the 3/2 with a 2/3 in front. So all those integration techniques are now viable, but we're still now just integrating with respect to one variable. And then we'd evaluate it from 0 to 1. So if we combine all of our coefficients now, we get 1 over 18 times 3 would be 54. And we plug in the top, and we get 37 to the 3/2 minus 1. So that's it. I'm going to stop right there. That's not a very pretty number. But at least we can get an exact answer. So when we pick up with vector calculus tomorrow, all we're going to be doing is instead of combining the x prime and the y prime into one slope, dy dx, we're just going to keep them separate. We're going to keep them separate, and we're going to look at horizontal component and vertical component, and we're going to write it almost as an ordered pair. We're going to write them, though, with chevrons instead of nice rounded parentheses. It's essentially vector calculus. Yeah, whenever you break something up into its two components, x and y, it's essentially vector calculus. But the style that we're presenting our answers in is not in vector style, okay? right. Have a great afternoon. See you tomorrow.